Hello, this is the first of two videos that I'm going to do on satellites, more specifically artificial satellites, which we've been launching since 1957, which is when Sputnik 1, the first artificial satellite, was launched. So in this video, I'm going to go through stuff to do with orbits, the different types of orbit, a little bit of the maths behind it all, pros and cons of the different orbits, stuff on escape velocity as well, I'll tag in at the end. And then in the next video, I'll go through a history of notable satellites. So all the way from the first one in 1957 up until stuff that's going on in the present day. So when it comes to artificial satellites, then you can break them up into a number of different groups, but I'm going to go for a simple split between the ones that are going to be in orbit around the Earth and then the ones which are being sent off around the solar system, to other planets or even beyond. We've got 5 or so satellites have actually left the solar system now. I'll talk about those in the next video. But let's start then with the ones which are actually orbiting the Earth. So if you've got an artificial satellite, something small orbiting the Earth, something big, then they're obeying Kepler's laws of planetary motion. And I know that says then for the first law that the satellite is orbiting the Earth in an ellipse with the Earth at one focus, but these are very low eccentricity orbits. So they're pretty much circular orbits, which means we can use our classical mechanics for circular motion and do a little bit of maths on that. So I'm going to start with this because these equations are going to be useful later on with a description. So let's do our F equals ma for circular motion, or as I've written here, an ma equals F. So this is our mass times our centripetal acceleration is equal to the force due to gravity between the Earth and the satellite. So let's then cancel the m's, the small m's, which is the mass of the satellite, cancel an r on either side, and then we can say that v is equal to the square root of gm over r. Now, this is, just to be clear what all of these mean, obviously we've got the gravitational constant there, capital G. R is the distance, is the radius of the orbit. So it's the distance of the satellite from the center of the Earth. That's what little r is telling us. Capital M is the mass of the Earth. And then V is the orbital speed. So you can see from this that if we want a stable orbit, because that's how we can do this circular motion calculation, we can only actually equate these two things into F equals ma if we've got a stable circular orbit. So if we want a stable orbit, then we need a particular v for a particular radius. So we need to get a specific value of the orbital speed in order to have a stable orbit at radius r. And you'll notice that this is independent of the mass of the satellite. So every satellite that's in a stable orbit at, say, an altitude of 500 kilometers above the Earth's surface will be traveling at the same speed. So it is mass independent. Now, this then, let's quantify some numbers on all of this then, because the radius of the Earth, we need to factor this in, because quite often we'll be talking about altitude of a satellite above the surface of the Earth. And of course, our r here is the distance from the center of the Earth, not the surface from the Earth. So radius of the Earth is around about 6,400 kilometers. It's a little bit less than that, but roughly speaking, 6,400 kilometers. So that's the radius of the Earth that we're dealing with. Of course, we know that G, our gravitational constant, that is one we're familiar with, is the 6.67 times 10 to the minus 11, and that is Newton meter squared per kilogram squared. You can see that, of course, from our this bit here. If you look at the units, do a unit analysis on the force in that equation, you can see what we're going to need in order to end up with units of force. We need to multiply by mass twice here. That's our kilograms coming in twice for the two masses. And then we've got a meter squared on the denominator. So that's G. We've got mass of the Earth, our capital M. That is a little less than 6 times 10 to the 24. So 5.97 times 10 to the 24 kilograms. So we've got that. Another thing we want to keep in mind, I spoke about this in the video on the Earth's atmosphere, is the thickness of the Earth's atmosphere. So we're certainly getting into the exosphere by the time we've got up to, say, 1,000 kilometers. So let's say that we've got some kind of divider going on, a difference between, if we're less than 1,000 kilometers, then we've got more atmosphere than if we're beyond 1,000 kilometers. And this is really what we're talking about for low Earth orbits. So a low Earth orbit is really, I mean, there's no definite dividing line as to what constitutes a low Earth orbit or a medium Earth orbit. But the low Earth orbits, let's say they're less than about 1,000 kilometers, give or take. So let's go with that. Right, let's get back to the maths then, because something else which is going to be useful, and I did this in a previous video as well, is let's combine this equation here with the fact that the orbital speed is also our distance over time. So that's our 2 pi r over t. Now, if we combine these two equations, this gives us Kepler's third law. You know, it's just a straight substitution to eliminate v and get t as a function of r. That then gives us that t squared is equal to 4 pi squared r cubed over gm. So that is our, as I say, Kepler's third law, which is that the square of the orbital period is proportional to the cube of the radius of the orbit. Now, this then allows us to think, well, what if we want to have a geostationary orbit? So what if we want the satellite to be orbiting the Earth at the same speed as the rotation of the Earth, so the same angular speed as the rotation of the Earth. So the satellite will stay directly above the same spot on the Earth's equator. If it was orbiting around the equator, it would just stay overhead at all times. So we can do a simple calculation on that for a geostationary orbit. So if it's geostationary, well, we know what the orbital period is going to have to be, because we want t to be 24 hours. 24 hours is 86,400 seconds. So we've got that as the square of our orbital period. We then need to multiply by g and m and divide it by 4 pi squared, and that is going to give us our r cubed. So that is giving us a specific radius of the orbit of a geostationary satellite. And this comes out as being, well, it gives r is 4.22 times 10 to the 7 meters. That is the distance from the center of the Earth. If we want the altitude, we have to then take off the radius of the Earth. So this is then giving us an altitude above the Earth's surface of around about 36,000 kilometers. So that is a long way up, especially when we're comparing this to these low Earth orbits, which might be less than 1,000 kilometers. So examples of that, the Hubble Space Telescope, that's around about 500, 550 kilometers. You've got the International Space Station is a little bit closer in than that. So it's around about 400 kilometers up. And that's why these things are orbiting around the Earth so quickly. They rush round. You've got geostationaries going around once a day by definition of what they're achieving. Whereas these ones in low Earth orbit, the International Space Station is zooming by. You can see here, if R is smaller, then V is higher. So they're really whipping around the Earth at quite a rate. Of course, another issue that you've got with low Earth orbits is that you're encountering more of the atmosphere. So you're getting more friction, you've got more resistance, you're going to get slowing down. And if nothing is done to maintain the altitude of the satellite, it's just going to decay down. It's going to spiral down and it will re-enter lower atmosphere and either burn up or crash to Earth. So you're going to need some kind of orbit and altitude control on, well, most satellites, but particularly the low Earth orbit ones. You have some kind of propulsion in order to maintain stable orbits, and you're going to want a power source. So most satellites have got solar panels on them as a power source, and then for propulsion you might have some chemical propellant that gets propelled out the back of the satellite in order to maneuver it, or you might get some electromagnetic propulsion, so accelerating ions through a potential difference. And then, of course, you've got Newton's third law coming into effect, and then that's maneuvering the satellite around. So you need a power source, and you need the orbit and altitude control. And of course, you need the equipment that's going to be on the satellites, depending on what they're doing. And depending on the use of the satellite, again, that's going to affect what sort of orbit you're going to choose. If you want to have something where you're in permanent communication with the same satellite, geostationary is great. You can put it over the same spot of the Earth. You can just deal with one satellite, but it's so much further away. If it's 36,000 kilometers up, you're going to get more lag on communication with the satellite. It's harder to launch up to that height as well. You need more energy in the launch. These are going to be bigger deployments in terms of getting the satellite into position, and you're further away, so you've got lower resolution. Now, you can solve a lot of these problems with low Earth orbits, but then they bring their own problems. Okay, you can get higher resolution and less lag on your comms time if you're closer to the surface of the Earth, but you've got a smaller field of view. If you've got the Earth and you've got a satellite there, well, you might just be looking at that amount of the Earth's surface. If you've got geostationary with the same angle that it's observing over, then you can cover a much larger area. So you've got issues with these low Earth orbits. Okay, you can zoom in on this small area with higher resolution, but it is a smaller area. Of course, you've also got these low Earth orbit satellites are not always going to be where you want them to be. These are zooming around. They're not always available to you from where you're located on the Earth's surface. So quite often now you'll end up getting constellations, is what they refer to them as, constellations of low Earth orbit satellites. You can have loads of these, but then you need to manage, well, which one is the one you're currently coordinating with, which is the one that you're communicating with at any particular time. So there's a bit more in the way of logistics of actually working out which satellite at which time, what is going to be available, what am I communicating with. So some constellations will be quite tightly packed. You'll get these big arrays. You might have seen some of the ones that companies like SpaceX have been putting up. I've drawn it as a grid, but these are satellites that are positioned relative to each other in a close area. Or you might just be coordinating between ones which are much more widely spaced out, and you're waiting for the next one to come into your field of view. So pros and cons on these different orbits. But even then, although we've got 90% or so of satellites are in these low Earth orbits or geostationary orbits, there are others that are in different types of orbit, which can be particularly useful, particularly if you're wanting to monitor the entire Earth's surface. These ones are all moving with the same direction as the rotation of the Earth. If you think of what it's like when you launch a satellite, if you've got the Earth, which is rotating from west to east, so as you look down on the North Pole, it's going to be rotating anti-clockwise. So there's a lot of angular momentum you've already got just by being on the Earth's surface. So it's a lot easier to launch satellites into orbits that are following the rotation of the Earth. But there are some times when you don't want your satellite just moving in that direction, because everything ends up being sort of near the equator, and it's just going round and round looking at spots on the Earth at the same latitude. What if you want to be looking at different latitudes with the same satellite? That means that we're going to want a polar orbit. So if you want a polar orbit, this is then orbiting through longitude rather than latitude. So it's going north-south rather than west to east. Or it could be going south to north, whichever way you want it to go. Now that requires more energy to get a satellite into a polar orbit, but yeah, it's really useful because you can then cover the entirety of the Earth's surface. You're covering all latitudes, and the Earth is just naturally turning beneath you anyway in order to cover the different longitudes. So yeah, you've got polar orbits as well, and you get variations on all of these orbits. You get things called sun synchronous orbits as well, which are similar to polar orbits, but they're then trying to maintain a similar level of illumination from the sun as the satellite is orbiting around. So you've got lots of variations, but the vast majority of satellites are in low Earth or geostationary orbits, or sort of mid-Earth orbits, so ones which are a little bit further up. But so they're in this range from say 400 kilometers up to these 36,000 kilometers, and mostly orbiting in the direction of the Earth's motion. Right, the other thing that comes up then, if we then move to these other satellites, the ones that aren't going to be in stable orbits, that we're actually trying to get out away from the Earth and into the solar system and beyond, these satellites are going to need to achieve escape velocity. Now, we don't need escape velocity, obviously, for satellites that are going to be going into an orbit around the Earth, because we don't want them to escape the Earth. We want them to be in a stable orbit. But if we don't want them in a stable orbit, then we want escape velocity. So this is where we're going to be doing a conservation of energy, of saying, well, our half mv squared, the kinetic energy that we're giving to the satellite, has then got to match the gravitational potential energy, which of course is negative, that we have when the satellite is on the surface of the Earth. So we've got kinetic energy supplied has got to be equal to the gravitational potential energy that we need to overcome in order to get out of the gravitational well that the satellite is in when it's on the Earth's surface. Because of course, let's go back, just recap our gravitational potential energy. If we've got the surface of the Earth with our satellite sitting on it, we're saying that 0 GPE is at infinity distance away from the Earth. That's where we've got 0. Anything closer is with negative gravitational potential energy, because the object is then gravitationally bound to the Earth in some way. So if we're going to get to escape velocity, if we're going to be able to get the satellite away from the gravitational clutches of the Earth, we need at least kinetic energy that's going to get our GPE back up to 0. So that's what we're doing here. And this is how we achieve escape velocity. So if we're just solving this, again, the m's cancel. Escape velocity has got nothing to do with the mass of the thing that's escaping. It's to do with the mass of the thing it's escaping from, in this case, the mass of the Earth. So this tells us that our escape velocity is the square root of 2gm over r. Now, you'll see this is very similar to the equation we had over here for the velocity in a particular orbit of radius r. So these r's are the same. So this is saying here, this first equation, the one in red over here, so that is the velocity of a satellite in a stable orbit at orbital radius little r. This equation here in blue is saying the velocity required at that orbital radius to escape. So and you'll see there's a multiple here of root 2. So let's just clarify this with some numbers. Let's take the geostationary orbit then. So in our geostationary orbit, if we work out the v that is moving at, so we can use either of these equations. We can use this one here, the root gm over r, or we can use this one here, the 2 pi r over t. They're going to give us the same answer. They're going to give us the same orbital speed for a satellite in geostationary orbit. And that comes out at around about 3,000 meters per second. So that is how quickly a satellite in geostationary orbit is moving. If it was going to escape, so no longer be in a stable orbit, but actually escape the gravitational clutches of the Earth, then it will have to move root 2 faster than this. So we've got that multiple of root 2 in this equation here. So we would have to do, if it was doing 3,000 multiplied by root 2 meters per second, then that would mean it would have escape velocity from that orbital position. So that is from that radius r, from that altitude of 36,000 kilometers, or that distance from the center of the Earth of 4.22 times 10 to the 7 meters. So escape velocity depends upon where you are, because it depends upon, where you are tells you how much GPE you've got to, supply from your kinetic energy. So if you were on the surface of the Earth, something on the surface of the Earth, again, we can do this calculation, 2gm over r square rooted, to say what is escape velocity from the surface of the Earth. So at the surface of the Earth, it's around about 11,000 meters per second from the surface, but it's around about, what's that going to be? That's going to be about, I don't know, well, 4,300, something like that. So 4,300 meters per second from the geostationary orbit point. So, we're already part of the way there. If we've got to geostationary orbit, then you need less energy. You need a smaller escape velocity from geostationary orbit than you do from the surface of the Earth. So you need to keep in mind where you're measuring from when you're looking at escape velocities. And we've always got that multiple of root 2. So any satellite in a stable orbit, work out how fast it's going, multiply that speed by root 2, and that is the escape velocity that it would need from where it is currently in stable orbit. Now, this has an effect on maintaining an atmosphere, just getting away from satellites for a moment, because this does link in to atmospheres as well. So, think of what's happening in the Earth's atmosphere. Say you've got some O2, so we've got some oxygen, molecular oxygen. So, and that's at, say, 20 degrees C. And then we're saying, well, that is going to give us our 3/2 kT, go into our ideal gases. So that is the energy that we're going to have for an oxygen molecule. That is going to be then equal to a half m, well, v squared. But of course, we've got a population, going back to our ideal gases. Remember, we've got a distribution of velocities of our molecules. And we've got our root mean square speed. Remember, we did this in ideal gases. So if we take that as our squared, then we can solve this equation for oxygen at 20 degrees C. Of course, oxygen O2 has got 32 nucleons. So that is going to give us our mass that we've got here. K is just the Boltzmann constant. T, well, is 20 degrees. So that is going to give us the RMS of the RMS speed of the O2, which comes out at around about 500 meters per second for O2. So that is significantly down on the escape velocity. If you've got something at the Earth's surface, if this is O2 at the surface of the Earth, well, 500 meters per second is a long way off 11,000 meters per second. And I know RMS means that we're taking an average and you've got a high energy tail, but there aren't going to be many O2 molecules which are going to be getting up to 11,000 meters per second. And even if they did, they're not going to be able to get to the outer atmosphere without colliding with something else and losing some of that energy. So we're not getting O2 just vanishing off into space, certainly not at that sort of temperature that you've got down near the surface of the Earth. Now, different if you've got helium. Now, there isn't much helium in the atmosphere, and helium has got, well, it's only got 4 nucleons, so it's going to be going 8 times quicker. So we're now up to 4,000 meters per second, even when we're just at 20 degrees C. Now, this is getting closer to the 11,000 meters per second. When you get to a high energy tail, you're going to start getting helium, which is achieving escape velocity. Plus, of course, if we then move up to higher altitude parts of the Earth's atmosphere, where you're getting more energy coming in from the sun anyway, you've got more solar wind activity, you've got more energy from the UV, which is, getting some pretty high temperatures from a thermodynamics point of view in the upper atmosphere, then this is why the Earth doesn't hang on to helium in its atmosphere particularly well, because it's moving around so quickly. Now, don't think, though, that the only escape mechanism for molecules in an atmosphere is they're not just thermal processes. It doesn't mean, anything which is below 11,000 meters per second purely from thermal effects will not escape, because you've got magnetic effects going on as well. If you get into the higher atmosphere, you've got more interaction between the Earth's atmosphere and particles coming in on the solar wind. So you're going to have ionized particles coming in on the solar wind. These might then ionize, well, in fact, they do ionize a lot of particles in the Earth's atmosphere. These can then get carried on the Earth's magnetic field and escape the atmosphere that way. The Earth's magnetic field, the magnetic poles, well, near the north and south poles in terms of the axis and rotation. And the Earth's magnetic field extends quite a long way out into space. So if you've got some charged particles, they can accelerate out of the atmosphere along the magnetic field lines of the Earth and then escape the atmosphere that way. So it's not just thermal processes that will get particles to leave the atmosphere. It can be magnetic processes and other things as well. So there's a whole range of ways that things can leave the Earth's atmosphere. But yeah, it's worth tagging that on, I think, in terms of escape velocity alongside satellites. So I think that's pretty much covered everything that I want to say here. We've gone through the different types of orbit if you're trying to get into a stable orbit, the pros and cons of low Earth orbits versus geostationary orbits versus polar orbits. Then looking, well, briefly at how you get escape velocity if you want to have satellites that are not in a stable orbit and are heading off to other planets or even outside the solar system, how you need that extra energy and the relationship there between the velocity, the speed you've got in a stable orbit versus the speed that you would need in order to achieve escape velocity, that multiple of root 2 that's turning up. And then consequently, off of the back of the escape velocity, how planets can hold on to atmospheres. And this is why with the smaller planets, because remember the escape velocity depends upon the mass of the planet. You can see here we've got that square root of m, which is in there. So the lower mass planets are going to have a lower escape velocity, so much harder to then hold on to an atmosphere. Particularly, you take something like Mercury, where it's really, really hot as a planet because it's close to the sun. It's so much less massive than the Earth. Well, there's just no way it's going to be able to hold an atmosphere because, well, everything's going to end up being above escape velocity just from thermal processes without even thinking about anything else. So yeah, a lot going on here, but that's covered the high spots of satellites, and then I'll be back in the next one just to talk about some of the famous ones that have been launched over the last 70 years or so.